All right. Hello, everyone. Thank you for tuning in to today's Corundum developer meeting. All right. Let's go ahead and get started. So I got just real quick announcements and then some status updates. So announcements, the next Corundum developer meeting will be on May 22nd, and the next Switch developer meeting will be on May 15th. So at least as scheduled, unless something comes up, that's what things are looking like. This is just, as scheduled. All right. So moving on to status updates. Got a couple of just brief mentions of a couple of bugs. The FIFO memory inference issue that's we've been made some workarounds for, but I don't think that's has yet been fixed on the Intel side. And then there's the FIFO, or not the DMA write done mux bug that was reported pretty recently that I have a fix for, but it needs a little bit of additional work. And then I got a few words on the driver updates and some progress on the new queue management side of things. I've been chipping away at that. All right, so the FIFO memory inference issue. This is just seems to be an issue with Intel devices due to a problem in how Quartus is handling MLabs. Intel apparently has this scheduled to be fixed in a future release. It's not fixed as of 23.1. But what I've done for the time being on Intel devices is I've implemented a workaround that prevents the MLabs from being inferred in the case where they have an output register where this bug is a problem, which seems to be only the case in the main AXI stream FIFOs. In the few other places where MLabs are used, they don't seem to have output registers or read enables. So it seems to work fine as is. So without having to do any additional steps for working around. And from all the testing that I was doing recently on Intel boards, I have not seen any of the hardware checksum failure messages after applying the workaround. So, this seems to be mitigated, at least for the time being. I guess we'll see when Intel decides to fix it on their end. Upstream in Quartus, and then those workarounds could be removed because obviously if we have a FIFO that's small enough to run on MLabs, it probably makes sense to do that instead of using the M20Ks. All right. So the other issue that was just reported relatively recently is a problem involving the DMA write done mux. And this basically what happens is that if there's multiple operations on different ports on the mux at the same time with a different delay between the different ports, then there's a problem with how the entries are pulled out of the internal kind of port mapping FIFO, and as a result, it causes a hang. So I've implemented an initial fix for this. It's not yet committed, but I did post it to the Zulip and the DMA channel, and we were talking about this. The fix, it adds one cycle of delay in terms of returning those write done pulses. So I need to see if I can remove that one cycle of delay. So I'm going to keep doing a little bit of work on that. Hopefully I'll be able to get that sorted out, later this week and get that committed. But it seems like it does build with that with the fix applied, and we're no longer seeing the hang that resulted from this issue. So yeah, hopefully I'll get that squared away completely soon. Moving on to other status updates. I did a bunch of work on the driver over the past couple of weeks here. The main thing that I was trying to do is to get basically dynamic queue allocation implemented. So the idea is that instead of all of the queuing being set up during the driver loading, during probe and whatnot, the idea is that the queues, all of the data structures and whatnot associated with those, and the ring buffers and all of that, that will be allocated only when you bring up the link. And then since that'll be done like at the NetDev level instead of at the interface level, then if you have multiple NetDevs on the same interface or whatever, then they can just kind of allocate what the resources that they need from the pool of available resources. So the way I'm doing that is using bitmaps. So the Linux kernel has some nice little, not really APIs, but data structures, and you can use bitmaps and you can allocate. They have a very convenient function call that will find a 0 bit in the bitmap, set it to 1, and then give you the index of the bit that it's set. So that allows you to, in a relatively efficient manner, keep track of which tags or indexes or ID numbers or whatever from some set are available for use, and allow you to allocate them. And then to free it, you just clear the bit again. So we have bitmaps for all of the different queue types, and inside of the net device, I've reworked things such that when you create one of these, it'll automatically allocate the ID, right? It'll allocate the CQN for the completion queues, or the queue number for TXRX queues, whatever, and then set up all of the registers and whatnot accordingly. So that's implemented, seems to be working great. Currently, that's in my development repo. That has not been pushed to the main line repository yet. So guys are more than welcome to start playing around with that. So there's no hardware changes required for this to work. The only thing that was necessary that I didn't have previously was the RX indirection table. So now that I have that, then it's possible to do the dynamic allocation. And then once I had that implemented, then I went and I added a bunch of new ethtool APIs, because now that you can very easily tear everything down and set it back up, it becomes very easy to change the number of channels. So I went ahead and implemented the channel parameter, or the get set channels API. And then I also implemented get set ring param, which allows you to change the ring sizes. Previously, we have a couple of ethtool, or not ethtool APIs, but module parameters, which were used to set the ring sizes. So those now kind of set the default ring sizes, and then once the interfaces once the net devices are registered, then you can change the ring sizes with the set ring param by ethtool. Except for the event queues, those are only set by the module parameters. And then I also implemented the get set RX flow hatch APIs, which allow you to edit the indirection table via ethtool. And I also implemented the get registers, which basically just dumps the register space. So yeah, that should, I think, make things a little bit more flexible. I also went ahead and now that we have the ability to change the number of queues dynamically with ethtool, I went ahead and implemented, I suppose, more sane default queue counts. So on RX, it by default will now go with the number of online CPUs for the number of queues. So if you have, 8 CPU cores with 2 threads or whatever, that'll show up as 16 online CPUs. So it'll use 16 RX queues in that instance, instead of however many are implemented. And then on the TX side, I decided to go with 256, which is, probably a more reasonable number, but that can be changed as necessary, and we can certainly revisit what's going on here if certain applications require different number of TX queues. For example, by default, there might be some other solutions to influence that besides set ring param after everything's brought up. So we could certainly add some more module parameters or something else, or maybe expose that in some way to the extension kernel module to affect some of these defaults. Another thing that I did is I improved the kind of the teardown sequence that's used when taking a link down, and I think also the setup sequence as well. I was having a couple of minor issues in terms of what looked like a large number of spurious interrupts being generated. And I tracked that down to kind of a sequencing issue. So made some adjustments to improve that. And then I also did some other cleanup. So I improved kind of the resource management of how all of the the numbers of queues and the offsets and whatnot are tracked in the driver. I used to have for each queue type I had like an offset count, and stride entries in a bunch of structs. So what I ended up doing is I created a new struct, which is just like an MQNIC resource. And then in there, that has just kind of generic number, stride, base address, whatnot. And then I just have one of those structs for each resource. And then that made it very easy to support the dynamic allocation because I just added that to the struct and added a couple of additional kind of internal APIs for resource management. So that cleans things up a little bit. And then another thing I did is I went through like a lot of the debug printing. Previously, I used like I think dev info, dev debug, dev error, that sort of thing. I replaced that, not all of them, but the appropriate ones with net dev info, net dev debug, etc., so that any messages that are printed are associated with the net device as opposed to just the overall PCI Express device. So, if you have multiple net devices associated with one instance of the driver, then you can tell that apart very easily because it'll include the net device name in the kernel logs. So lots of cleanup stuff should make the driver a little bit nicer and easier to use. I have checked the performance after making these changes, and I haven't noticed any major changes in performance. So this at least doesn't have a significant detrimental effect on the performance. So, I guess whatever testing I'm doing, the bottleneck is somewhere else. So that's going to be pretty good, I think. All right. Now moving on to the queue management. I'm in the process of kind of reworking a few things in the queue management logic to in a gear up to implementing like queue pairs and implementing the variable length descriptor support and whatnot. So there's a couple of aspects to this. One of them is I'm trying to get rid of shared logic across multiple queue types. So combining the TX and RX completion queues, and also hopefully combining the TX queues and RX queues into queue pairs. And part of this is support dynamic allocation of queues. So like I just mentioned, we're capable of doing that with the current hardware. So I've gone ahead and implemented that in the driver such that, I have to do, fewer modifications and whatnot to make everything work. And I'm also going to separate the completion and event write logic such that we can use, relatively simple logic to write the events and, more complicated logic that supports batching and whatnot for the completions. So let's see. I think I've showed these slides before in terms of the queue state storage. This is how it looks right now. Just for reference, going forward, I'm going to go with something more like this. So we're going to shave off 12 bits from the base address field, which forces a 4K alignment, but then we can use those bits elsewhere. For the queue pairs, we're going to basically double up on the all of the internal pointers and indices, which means we basically amortize the base address register over both the transmit and receive portions. And then we're going to add the VF index and the LSO offset. And this one fits into so the CQ and the EQ, that fits into 2 URAMs, and the queue pair fits into 3 URAMs. And there's still a couple of additional bits, left over, because this ends up fitting into RAID 128. So got about 9 bits left, and this one fits into 192. So got about 5 bits or so left for other stuff. So we'll see. We may need to make some adjustments to this, but that's kind of what I'm looking at for the moment in terms of the queue state storage. And then I have been doing some work on the actual queue control registers. So for the CQ and the EQ, this is what I think I'm going to go with. I've gone ahead actually and implemented the kind of the new register layout in my development repository just to make sure that everything is working. And there's a couple of main changes that I'm doing here. One of them is obviously I've compressed this down into 16 bytes. So that means we can fit twice as many CQs in the same amount of address space. And second, most of these registers are read-only. Well, I guess 2 out of the 4 are read-only. And then I have some commands, which I just have a summary of in a couple of slides, which are used to update the queue state. So instead of doing like read, modify, write operations to, set the enable bit or set the arm bit or whatever, or instead of doing read, modify, write, you can always just kind of keep a copy of the register, make your modifications locally in software, and then write the new value. Instead of doing stuff like that, you can just blindly write these commands, these encoded commands to the control and status register or whatever to atomically change the state, right? So you can set enable bit, clear an arm bit, update pointer, whatever, just by writing these commands. So relatively straightforward setup. So more details on that in a minute, but this is what we're looking at for the CQ and the EQ. It's basically the same stuff that we have now, but compressed. For the TXQ and RXQ, I'm making the layout slightly different. This gives you more bits in the CQ end and also in the control and status. Potentially, if more stuff needs to be squeezed in here at some point, we'll have some room for that. But the fun part about this is we can take the bottom 3 registers and duplicate that to get the Q pair. And this takes up 32 bytes for the send queue and the receive queue, with the shared base address pointer for both. So the idea is that in host memory, you would have the SQ and the RQ ring buffers right next to each other, pointed to by that base address. So there are a couple of semantic related things that I got to figure out. Probably we're going to have to tie the enable status of the 2 queues together. If you want to use the queue, then you set the size to a non-zero value. If you don't want to use the queue, then you set the size to 0. And then it'll probably be the SQ ring and then the RQ ring basically adjacent to each other right after the ring buffer. And then if you're not using the SQ, for example, then the RQ ring would appear right at the base address. So got a few details to figure out here, but that's kind of how things are looking at, or this is kind of what I'm planning on doing with the Q pairs. And yeah, so 32 bytes, which I think is the same size of one TXQ or RXQ in the current setup. So improving the density effectively. So the idea is that if we take a particular block of memory, register space on the NIC, cut that in half, you can put your Q pairs on one side and the completion queues on the other side, and you'll have one completion queue for every send queue and every receive queue. So that's kind of the philosophy that I have with these layouts. And I have not implemented the Q pair setup yet, but I've implemented the other ones in my development repository. And these are the commands that I have put together so far for controlling them. So we have set VFID, set size, set CQN, EQN, IRQN, depending on the queue type, set producer pointer, set consumer pointer, set enable, set arm, and then we also have kind of a combined operation, set consumer pointer and arm. So I've not implemented this one in the driver yet, but potentially if you're doing a user space driver or whatever, this could be useful. When you're processing a completion queue or an event queue and you update the consumer pointer on the hardware, instead of doing a separate set consumer pointer then set arm, you can just fire off one command, which is it sets the consumer pointer and then also rearms the queue at the same time. So that's the kind of fun stuff that you can do with the encoded commands. You can kind of code for multiple operations potentially with one of these. So for the most part, these are just influencing the queue state, but potentially, more commands could be implemented that do other things. We probably will at some point with the queue pairs have to implement some additional stuff, but we'll cross that bridge when we get there. So let's see, getting to the status on all of this stuff. I've implemented the new layouts for the EQ, CQ, TXQ, and RXQ in my development repository and updated the driver, test bench, whatnot accordingly to make sure all that works and tested it in the hardware. I've merged the TXCQ and RXCQ into a single CQ. So I guess one thing that I didn't mention before is with the updates for dynamic queue allocation, I've kind of added some additional odds and ends that I'm going to be removing later. So there's like some is TXCQ field in there and a couple of other things that are necessary to manage the separate TXCQs and RXCQs. But if that can all be pulled out of the same pool, then you don't need that. And those little bits can be removed. So once I implemented this, I removed that and everything works great. I also went ahead and split the completion event rights into separate instances. For right now, it's the same logic, but what I'm working on next is basically resurrecting the batched completion write logic that I was putting together. Boy, I think that was last year. Time flies. I've updated that to work with the new register layout for the CQs and the EQs. Well, except it's not going to handle the EQs, so only care about the CQs. I've also removed the pointer write back logic that I baked in there previously, because we now are going to be using the phase tag setup. I'm working on getting that piece implemented. It's slightly non-trivial because the phase tag bit is kind of coming from a different source than the actual completion, but they have to be glued together and then handed off to and then written at the internal memory and then handed off to the DMA engine. So I have code to generate the phase tag bit. Now I just need to attach it to the completion. So progress is being made here. And then next up, once I get that operational, is to work on new descriptor fetch logic and to merge the TXQ and RXQ into the Q pair SQRQ and get all of that operational in hardware. So, and I think as part of this, we'll also implement the variable length descriptor support, which hopefully will improve performance, but either way, it's going to improve flexibility going forward. All right, so that's all I got in terms of status updates for today. If anyone has any questions or comments about any of this, fire away. Looks good to everybody.
So maybe not directly to this precisely,
Yeah, sure.
just in the end, but maybe more concerning the pull request we sent over, or I sent over a while ago, concerning the enablement of the KR260. I was just wondering. So take your time to review this. No worries.
Right. Yeah, I keep forgetting about that.
No.
I need to review all. There's probably a few pull requests that I need to review. Yeah, but sure.
I was just asking because, and again, you mentioned at the beginning that you need to save some time to test things out with the KR216. That's totally okay. Happy to support. But I was more asking concerning. So we were thinking of expanding that initial pull request with maybe one or two more. Second one would probably be an expansion of the existing pull request involving essentially an extension of the Ethernet Verilog current value proposition with additional configuration on the PS to make sure that you can use HPM0 essentially for passing over information from the PS to the PL, which is then used in the PL to do DDR exchange with the PS. So we've essentially extended the current implementation based on existing other reference designs to let's say make a 10 gig NIC which can do DDR exchanges with the PS. So we were just wondering, that's something that for us is very useful. It took us.
You're talking about a 10 gig NIC. This is using the UDP stack, or this is using Corundum, or
using the UDP stack.
So this is not really a full NIC that can do anything, but it's more specific to UDP specifically.
Yep. Yeah. I mean, it's leveraging also in the PL the MAC layer, of course. So even though it's not exposed at the user space as an official NIC, I guess it can be used as a network interface to exchange data via the PL.
Right.
So maybe it's just a lack of precision in how I'm using the NIC wording, but that to me, the fact that it can already exchange networking data throughout the PL, that to me, I guess, qualifies for naming it a NIC.
Yeah. Okay. Right. So, right. I'm just trying to figure out what is being added to this aside from kind of the core, UDP stack that's present in all of the example designs. So we're extending this with connections to the the processing side of things, to the
Yeah.
ARM cores. So you can, instead of just doing the UDP loopback, you can actually send and receive traffic from software.
Correct. So instead of essentially leveraging the Linux networking stack, which is what we discussed in the past, you're using the UDP IP also offloaded in the PL, and then the payload is just being passed over DDR. So
Right.
nothing terribly fancy, but still maybe a reference design that could be useful for anybody else looking into doing such a thing. So we were just wondering if this is something that could be interesting for the Verilog Ethernet repo. And if so, how would you propose we send it over? Maybe in a subfolder within the KR260 reference design examples with an underscore DDR
Yeah, we
appended.
could, yeah, something like that would probably make a good bit of sense. It'd be useful at least to kind of take a look at what it is that you've put together and just see what it looks like and if it seems like it's appropriate. I mean, it seems like it would probably be an appropriate example design, right? Because we're actually attaching some additional logic basically to the UDP stack. So it seems pretty appropriate to me. So
Okay, well, we'll do
um,
that. As suggested, we'll just follow the same nomenclature you've said, and then send it over. Again, what we plan to contribute at this phase is something super rudimentary, very minimalistic, just
right.
passing the payload. That's it, super straightforward, and more complex things are being done right now, such as using ring buffers and so on and so forth to manage a bit more how payload gets passed over to the PL. But yeah, that may or may not land into the main repo. But I think as for contribution, we'll look into that, and then so once maybe, or yeah, I'll probably wait until you have a first review of the existing PR, and then I think we'll send a second one.
Yeah. All right.
Okay. Good.
Yeah, and I mean for the naming, it's the 10G versus 1G versus whatever. I think it's mainly in terms of the link rate. So what we could do is add another underscore after that, like you could do like FPGA 10G Zinc or
Yep.
HPS or PS or whatever to indicate that we're bringing the ARM cores into the picture as well. So, but yeah,
I mean,
I
I'm
think
asking because
that could be pretty useful.
I'm terribly bad with naming. I know engineers overall we're bad with naming. Make it
There's a
short.
joke about that, right? The
Yep.
hardest part's of computer science, right? Caching, naming things, and off by one errors.
Yeah.
One question from my side: how's your interface planned to be in the software side? So is this a socket-like API or character devices or something?
It's a really good question, Ulrich. Yeah, that's the end goal. So it's gonna be essentially I cannot commit to have a 100% LNS socket compliant API, but to a certain extent, our use case has some requirements of supporting some of the system calls typically used with a Linux networking stack. So yeah, rather similar to that. But again, those
Okay.
layers may or may not land into this initial contribution. But for now, yeah, that is the intention.
Okay, interesting. Yeah, we might want to talk offline again, I guess.
Yeah, just hit me. I mean, you know how to reach out?
Yeah, I guess you're on Zulip, right? So then we can just chat.
Yep, I keep forgetting about that.
Me too. Okay, cool, great.
Yep.
All right. So anyone else have any questions or comments about anything or anything that people want to discuss?
Maybe a quick silly question, since you touched on it at the beginning. Intel, I think you mentioned that you're working on the AGLX series. That's something also we've been working on a side project. Just curious, how does it build? Like, what do you produce out of the make process for Intel? Do you produce an RBF, which then you use to get into the SD card image build process?
So we haven't actually taken a look at the HPS side of things for Intel yet. Everything I've been doing has just been direct on the FPGA side. So I've never looked into like doing an SD card boot or anything like that. So the make file just produces the soft, and then I probably have some code to in some of the projects to convert that to like some sort of a flash image. I know that that Ulrich and whatnot are doing a lot more work with the Stratix 10 devices than I have there, because their product is using one of those. So I'm not sure if they have any modifications and adjustments to the build process. But for me, I just get a soft file and then use the programmer software to load it onto the board. The other problem that I've run into is that with a lot of the Intel boards, the process of getting something into the flash can be very different and very board specific. Unlike the Xilinx stuff, where on most boards the flash is just directly connected to the FPGA, on the Intel boards, on a minority of them, that's the case. On all the other ones, the flash sits behind a different FPGA. So there's going to be kind of a main FPGA, you know, Stratix or Agilex part, and then there's going to be a kind of a secondary FPGA that is part of the process of getting the firmware loaded into the main FPGA, usually some sort of a Max 10 or something. The flash sits behind that. So that means accessing the flash now becomes highly board dependent because you have to go through that Max 10 FPGA. So on some boards, the only way to load firmware into the flash is via USB JTAG. On other boards, they'll have some custom protocol between the two FPGAs that allows, you know, the main FPGA to access the Max 10 and the flash through that. So on those boards, you know, you would have to do something custom if you wanted to, you know, reflash via PCIe. And then on the good boards, the flash is directly connected, and you have to go through the SDM, but at least that's standard. You know, if you're on a, you know, you have to do that on any of these newer parts. So there's some sort of mailbox FIFO something mailbox interface for talking to the SDM, which apparently is not super straightforward. I know the MLE guys have been working on that.
Yes.
We're getting a lot of noise from somewhere, I guess.
Yeah, that's me. I'm on the way home, basically.
Okay.
Getting late. Yeah, but actually, so we try to be on the good side. So we directly attach the flash on the SDM, and we have software available to update everything through PCI Express using our internal head of development. And we do plan to provide this code. It's not a performance optimized implementation, so we are just running a like super simple register map of the register map that they provide for this FIFO indirect. So we have a double indirection here in this case, but it works, and we can also do something like reading out temperatures, voltages. Yeah, do everything what the SDM wants or lets us do, let's say.
Only what you're allowed to do, yeah. Sounds
yes,
about
and,
right. But I mean,
and it somehow depends on boot modes, actually. So there is this remote remote firmware update procedure, and you can only use this if your image originally uses this kind of boot type, and otherwise all the commands just return with errors, which is fine because it's documented and as well. But yeah, so if you're interested in this code, like until we want to push it to public, because we are just internally reviewing the software portion of it. The hardware is now part of our internal releases for like a couple of weeks or months, actually. So this is running fine.
Okay, well, I mean, that's fine. We can certainly take a look at that when you guys are ready. But yeah, it sounds like there's a few more considerations than I had originally thought. Okay, well, it's nice to know that that you guys are making it work. So
yeah, and maybe to close the loop with the file formats, we use the RPD format, and we have some additions to the make file that actually produces it, using a configuration file that we need to put together for the board. And then
RPD?
I guess so, yes.
Oh, this is for the Intel RPD. Okay.
There are so many binary files, but I guess I got it right. Anyway, you need a config file to generate those.
The raw programming data. Okay.
Yeah,
And then you need to swap bits and everything, and then it works.
there's quite a bunch of binary formats. The soft that Alex, you were mentioning before, that's good enough. On the soft, you can produce the RBF that I was asking for. So we're good. We're good. Just tons of binary formats.
Yeah, so
Fine,
maybe there was so much stuff to do. So I think I see if we can kind of pull this in and see whether we can provide an early access kind of preview of the code.
I didn't hear what you said a moment ago, Victor, because of the noise. So what were you saying?
Sorry, I was saying that you essentially answered my question because you pointed out that you're producing the soft file, the SOF file, and then you can produce the RBF file that I was asking for out of this soft file. And I was just emphasizing what you both said, you and Ulrich, by saying that there's plenty of binary formats and it can get very confusing. So yeah, I actually, as a side note, I keep pretty handy my acronym glossary while working with Intel boards because there's so many, and I keep learning about them pretty much every second day about a new one. So and the list is quite extensive already. So yeah, not getting surprised anymore.
Intel really likes their alphabet soup and their TLAs. If you're familiar with what a TLA is.
Yeah.
All right. Yeah, I mean, I've definitely heard of the RBF files, but RPD is I'll have to take a look at exactly what that is. Anyway, yeah, I know it's depending on how you want to do the programming, there's one of any number of files that you can generate. And I think the SOF is kind of the equivalent to a Xilinx bit file. It's kind of the lowest level one for the FPGA side, and then you could generate all sorts of stuff based off of the soft file. And then yeah, it's not hard to script that with the make files or whatever to make whatever you want. I guess where stuff gets complicated on the Intel side of things is it's not like you just write the bit file to the flash and then you're done. They have, you know, header formats and various flash layouts and stuff for various purposes, just to make things more complicated. Yeah, that's not a can of worms I've you know, fully opened up yet and familiarized myself with. But I know for doing the flash updates on the Intel devices, it's going to be a little bit more complicated, not just in terms of accessing the flash itself, but in terms of, you know, what needs to go where. So I know this is something that I've kind of brought up a couple of times, but it might make sense to try to cook up a firmware update package format. I don't know if there's anything kind of out there that people are using, but I'm thinking like a combination of like a manifest file plus, you know, several other binary files in some sort of an archive that would describe, you know, what needs to be done for a firmware update, including, you know, all of the necessary binaries. So the manifest file could say like for a firmware update for the you know, main firmware, you got to write this file to this offset and that file to that offset and whatnot. And then if it's just a text manifest file plus some binary files in an archive format, I don't know, like a zip file or a tar gz or something, then it would be pretty easy to script the creation of that as part of the build process. So you can, you know, run make and you get your firmware update file ready to go. So I think I created a GitHub issue to discuss the firmware update format, but there hasn't been any movement on that. So I don't know if anybody has any opinions at all, one way or the other, or if there's any, references, other projects doing similar stuff that we can take a look at that anybody's aware of. That would be nice. That'd be nice to know about. I can post a link to that since we're discussing it. Let me dig that up real quick. I think I just kind of laid down a few thoughts, more or less what I've just discussed on that issue that I created. There we go. That's where it went. Okay. There is the issue. It's issue 130. There's the link. Put that in the chat. So yeah, if anyone's aware of any kind of existing implementations for, other projects for other hardware that has to have firmware loaded into it, anything that we can use as a reference, that would be cool.
I mean, this is on itself a fantastic project, and as far as it concerns us ourselves, we don't know of any of such projects, at least that has the courage to attempt to tackle heterogeneous accelerators. That's not something you see very often. And frankly speaking, when clients and people ask us about, hey, do you know about a project that mixes, the same accelerator for various target like vendors, we typically point people to this project. So yeah, I'm sorry if we cannot add in there, but certainly we may have some cycles on our side. If people in here has some ideas to try to start implementing something alike, because frankly speaking, this is a pain we often encounter ourselves in our work. We work with lots of accelerators, and not just restricted to FPGAs. We also work with other types of accelerators. And frankly speaking, it's a big pain. So thumbs up for this issue, and if it keeps moving, we'd love to get involved. That's all I can say.
Well, I'm wondering, it's the kind of thing where it seems like there could be maybe even some sort of a standard, or maybe a need for a standard that kind of defines, what something like this might look like. Just in terms of, because I know this is a common thing for other pieces of hardware. I know, like, if you're updating the firmware on, say, like a Mellanox NIC or something like that, it doesn't necessarily overwrite the entire flash. It's going to overwrite, certain portions of it. So, they must have some internal format that's kind of doing something similar. So this is definitely not specific to accelerators, but really any kind of hardware that has a flash chip in there somewhere is potentially going to run into this. And possibly this could be important for, if you have a Zinc device where you have eMMC or something like that, this sort of thing could play a role there as well. So definitely something to think about. I just want to make sure that if we are going to put something together, that we are kind of as forward looking as possible, so we come up with something that's going to be useful for Corundum going forward, and potentially for other stuff as well. So anyway, definitely a point of longer term discussion.
Yeah, this would be fantastic. Not aware of anything alike, but certainly very useful.
Well, all right then. All right. Well, I don't know if anyone else has any questions or comments or anything to add, or if not, then we can adjourn for today. Nope. I guess going once, going twice. I guess we'll adjourn for today and see everybody in 2 weeks. So I guess we have the Switch meeting in a week. So if people are interested in Switch, welcome to tune into that. Otherwise, I'll see you guys in 2 weeks. And the dates were there in the slides right at the beginning. I think but the 15th and the 22nd, I think it was. Yeah, so 15th for the Switch meeting and the 22nd for the next Corundum developer meeting. So see you guys then. Thanks
All
for
right.
tuning in.
Thanks, everyone. Ciao.